Let's move on to some of the applications of definite integrals in chapter number 7. And one of the first kind of applications that does come up for definite integrals has to do with the concept of volume of solids at revolution. And one of the very first problems in that category is something called the disk method. Now the disk method has to do with finding the volume of a cylinder. And you may recall in class that when we have a cylinder, we can find the volume of a cylinder using like a formula from like grade 8 math, where the volume is pi r squared h. And one of the reasons why we call it the disk method is because we kind of take a look at one subsection of the cylinder. And what we do here is we try to find the volume of one of these smaller cylinders. And since it's small, we call this a disk. And if we can find the volume of one of these disks, then we can find the volume of the entire shape by simply integrating from top to bottom or from left to right. Okay, so the disk method has to do with finding the volume of a cylinder, and then once we apply some integrals to that, we can find the volume of the entire shape. Okay, so let's take a look at the first problem, and let's just see if we can figure out what's happening here. Okay, so for this problem, I need to find the volume of the solid that's generated when the region enclosed by the following curves is revolved around the x-axis. Okay, so let's take a look at our function here, y equals to x squared. Now that's a parabola. And let's go ahead and start with the parabola here. Here's y equals to x squared. And this parabola is actually bounded by these two x values, x equals to 1 and x equals to 2. So let's just say that here is x equals to 1 and here is x equals to 2. So this region right here, that particular region right here in green, this is going to be rotated around the x-axis. And this y equals to 0 is just kind of emphasizing that we need to kind of stay in this region of y equals to 0. And we're going to take that green region and we're going to simply rotate it around this axis here. Now, once we rotate that green region, it's going to form some kind of solid. And our goal is we need to calculate its volume. Okay, so let's take a look at a few of these visual diagrams to kind of help us understand what that solid will look like. And then we will go ahead and apply the disk method and calculate its volume. Okay, so this is another diagram of what's happening. This is basically the equation y equals to x squared, but we're only focusing on x equals to 1 to x equals to 2. And you may recall from the previous diagram is that this blue region is simply the same thing as the green region that I highlighted in the previous on the previous notes there. So if I go back up, this green region right here is being highlighted as this blue region right here. And that blue region, that enclosed area, is being rotated around the x-axis. And if you do that, I kind of get this visual diagram right here. So as you can see, there's some symmetry represented by the green region. And as I keep on rotating this around like an infinitely number of times, it creates a solid. Now, if I take an overhead look at that visual diagram, this is the shape that's kind of being generated. So this is kind of a 3D image looking from top to down on what kind of object is being formed here. So that's an overhead view, and this is another overhead view of what this object could kind of look like. So it kind of looks like a sideways bowl, and our goal is to find the volume of that sideways bowl. Okay, so let's go back and take a look at a front view of this particular problem here. And as you can see, there is this sideways cylinder right here. That's called my disk. All right, that's my disk right there. And the goal is I want to write the volume for that particular disk. And if I know the volume for that one particular disk, I can find the volume of the entire solid by simply integrating. All right, so let's go ahead and write out what the volume is for a cylinder. So the volume of a cylinder, as started at the start of this video, is pi r squared h. Okay, so if I take a look at this disk here, this sideways disk, this height right here, I can call that dx. All right, so it's like the distance, the difference in the x values. So the height here is going to be dx. Okay, so let's go ahead and update our volume formula now that we know that the height is going to be dx. So this will be pi r squared. and the height is now dx. Now let's focus in on the radius now. The radius is pretty much this distance right here. That's my radius. And if I think about this point right here, that's really a y value. Right, so the radius is really this y height right here. So I can now update that into my volume formula. So now my volume is going to be pi y squared times dx. Now we're almost done here. We just need to, we're almost done our setup here, and now we have to figure out what does y equal to. Well, in the original problem, y was equal to x squared. All right, so what we have to do now is we will replace y with y squared. And if I do that, that's going to be pi times x squared. And then there's a power 2 there, so that gets raised to the power 2, and then dx. Okay, so that is the volume expression for one disk. And if I simplify this, this is 2 times 2 is 4, so that's x to the power of 4 times dx. And then there's a pi right here. So that's the volume expression for one disk. And if I want the volume for the entire solid, I can just simply integrate. And where am I integrating from where to where? Well, if I go back to my diagram, the question pretty much tells you that you are starting from an x value of 1 and you're ending at an x value of 2. So you're integrating from 1 all the way to 2. This is going to be 1 and that's going to be 2. So that is your volume formula for this particular disk. And so far this looks pretty good because if I have a x here, that means everything in between has to be written in terms of x. So this integral is ready to be evaluated using the fundamental theorem of calculus. So if I find the antiderivative now, that's going to be x to the power of 5 divided by 5, square boxes from 1 to 2, and then we have a pi in front. And this should give us the volume of the entire shape now. All right, so now we need to evaluate our upper and lower bounds. We always start with the upper bound first. So that's going to be 2 to the power of 5 divided by 5. And then the 1 now goes in. So that's going to be minus 1 to the power of 5 divided by 5. And after that, I can close the brackets. And then from there, let's go and evaluate this. This is going to be pi. 2 to the power of 5 is going to be 32 divided by 5 minus 1 over 5. And the final answer here will be 31 divided by 5 times pi. So that's my volume of the entire object that was generated by rotating y equals x squared over the x-axis. So if I go back to some of these 3D visuals, the volume of this shape is going to be 31 over 5 pi. Just before I move on to the next question here, if you're looking at this object from an overhead view, I guess this would be the 1 value right here, x equals to 1. And if this is like the top of that could be your radius right there, and perhaps you're going all the way to 2 there. So that was kind of like a visual. If you take a look at it from an overhead view, that's where you would kind of plant your 1 and your 2 and your radius. Other than that, you're just plugging the numbers into your volume formula and you're just integrating. Okay, let's move on to the next one. All right, if I move on to example number 2, I need to find the volume of the solid rate generated when the region enclosed by the following curves is revolved around the y-axis, the x-axis here. Okay, so my equation is y equals to 1 over the square root of x. I'm bounded by x equals to 1, 3, and y equals to 0. So let's go ahead and kind of sketch this, and let's figure out what we're kind of let's take a look at what area is actually accumulated, and let's just see what area that needs to be rotated around the x-axis here. So if I take a look at the graph 1 over the square root of x, that's going to look like something like this. So that's going to be y equals to 1 over the square root of x. And we're looking at the x values of 1 and 3. So here's 1 and here's 3. And the question also is kind of reminding us to kind of stay within this horizontal boundary right here. So if I consider all those equations there, the area that's being accumulated is this region right here in green. And we're going to rotate this around the x-axis as instructed in the problem there. Okay, so I'm going to rotate this object around the x-axis. So let me go to a few more visual diagrams on what's happening when I rotate this around the x-axis. And let's take a look at the solid that's generated, and then we will go ahead and calculate the volume. Okay, so let's take a look at a few more visuals here. Here's my first visual. So as you can see, this is an x value of 1. This is an x value of 3. So that part of the graph there, this is part of the graph of 1 over the square root of x, and I'm only focusing on this red region here, and I'm going to rotate that part around the x-axis. If I do that, you'll see that we do get this region right underneath it that's symmetric, so this region right here, completely symmetric to the top right here. And now let's go ahead and take a look at a 3D view from top to bottom. So this is what the object would kind of look like if I kind of rotated it around the axes, and I'm looking at it from like a bird's eye view from top to bottom. So it's kind of like a sideways cup there. So that's kind of like the 1, and this is the 3, and I have a sideways cup there. And just remember, the goal of this problem is to find its volume, and I'm going to do that by calculating the volume of one of these so-called disks inside. And once I have the volume of one disk, I can find the volume of the entire shape by integrating from 1 to 3. Okay, so here I think that's it for the 3D visuals. Okay, so let's go ahead and take a look at a front view of this object again. So this is the x-axis, this is the y-axis. Remember, I'm rotating around the x-axis here. And let's take a look at this disk that's kind of already pre-drawn into the problem here. So this is my disk right here. And this height right here, that's going to be dx. Right? It's the difference in x values. So if I go ahead and write my volume of one cylinder, that's going to be pi r squared h. And my h is now going to be the dx. So let's go ahead and update my volume formula now. So the volume is going to be pi r squared times dx. And after I have my height there, let's go ahead and figure out what's going on with the radius. Well, the radius is just this distance right here. That's the radius, right? And if I look at the top point here and the bottom point right in the middle there, if you think about that in terms of like the variable or the equations, this is really a y height, right? So the radius just takes on the variable y. So my new volume equation will now be pi y squared times dx. Okay, so that y will now be my new radius. Okay, and after that, you might ask yourself, okay, what is y? Well, if you go back to the original problem, y equals to 1 over the square root of x. So that will replace y now in my volume equation now. So volume equals to pi, bracket 1 over root x, all to the power 2 times dx. And if I go ahead and simplify this, this will be pi times 1 over x times dx. So that's the volume of one disk, and if I want to find the volume of the entire shape, I need to integrate the whole thing. All right, so where do I integrate from where to where? Well, let's go back to our diagram here. Let me just erase all this. Basically, we are integrating from an x value of 1 all the way to an x value of 3. So my lower bound is 1, my upper bound is 3. So I put a 1 here and put a 3 there. And now we're ready to integrate this. If this is dx, everything in between is in terms of the same variable, which is x, so that's good. So let's go ahead and find the antiderivative of this. The antiderivative of 1 over x is ln x. Right? The antiderivative of 1 over x is ln x because the derivative of ln x is 1 over x. And then I can put my boundaries in here. My boundaries are going from 1 to 3. And my constant pi I will leave out in the front. And let's go ahead and finish this problem off using the fundamental theorem of calculus. So this would be ln of 3 minus ln of 1. Okay, so all we're doing is we're taking our upper bound, plugging that in. We're taking our lower bound, plugging that in. And we know ln 1 is going to be 0, so my final answer is pi times ln 3. So that's the volume for that particular shape. Okay, let's move on to the next question in this section. All right, let's take a look at the next question here. I need to find the volume of the solid generated when the region enclosed by the following curves is revolved around the x-axis. All right, so here's my function y equals to e to the power of negative x. So let's go ahead and sketch what that would look like. Y equals to e to the power of negative x. That has a y-intercept of 1, and it's just kind of going down like that. All right, and after that, I'm bounded by x equals to 0, x equals to 1. So here is 0, here is x equals to 1, and I also have y equals to 0. So that's just a reminder that I need to kind of rotate around the x-axis right there. And this green region, that's the region that's going to be rotated around the x-axis, which is highlighted by that purple line. All right, so let's take a look at a few more visuals to see what kind of shape is being generated here, and then we will go ahead and calculate the volume of that shape using the disk method. Okay, so here are a few more visuals here. Let's start over here. This is basically, just use a different marker here. This is going to be 0. This is going to be 1, and this equation right here is y equals to e to the power negative x, bounded between 0 and 1. And then if I rotate this around the x-axis, let's take a look at the next diagram for that. So once I rotate this around the x-axis, I have a very of a similar object that's symmetric to the object in blue that's being formed. And then let's take a look at this from a bird's eye view. And here's my first image of this particular object right there. So it's kind of another sideways cup. And here's another visual of this sideways cup as well. Okay, so this is 0, and that's going to be 1 right there. Okay, so if I go back to this diagram right here, our goal is if we can find the volume of one of these disks that's inside this 3D shape, I can find the volume of the entire shape by integrating all the way from 0 to 1. All right, so that's the idea, just like the previous problems. Okay, let's take a look at a sideways view of this particular object here, a front view here. So here it is again. And my volume equation is volume equals to pi r squared h. That's the volume of a cylinder. And I know that this particular region right here, this is the height of this sideways cylinder. So that height is going to be dx. So the difference between the two x values. And if I go ahead and update my volume formula now, that's going to be volume equals to pi r squared times dx. Okay, after that, let's take a look at the disk a little bit closer here. I can definitely see that this part right here in red, that is my radius. That's my radius of my sideways cylinder, which is a disk in this case. And ask yourself, what is this particular height here? Well, this is just a vertical distance of y. So my radius is really the y variable. Okay, let's go ahead and plug that in for my radius here. Okay, if I do that, my volume is now going to be pi y squared times dx. Then ask yourself, what does y equal to? Well, the original problem has y equals to e to the power of negative x. So let's go ahead and substitute that in now. So this is pi bracket, so y equals to e to the power of negative x, all to the power of 2 times dx. Now that's the volume expression for one particular disk. If I want to find the volume of the entire object, I need to integrate this. All right, so where do I integrate this from? Well, we just read the original problem. We're actually integrating, let me just erase all this here. This is going to be from 0 all the way to 1, so I'm going from a 0 to 1. And let's go ahead and update my formula one more time. This is going from 0 to 1. And that right there is my volume expression for that entire 3D object. Okay, one more thing that I would recommend is maybe it's best to multiply the two powers there. So that's going to be e to the power of negative 2x times pi integral from 0 to 1 times dx. And volume equals to that. Okay, let's go ahead and find the antiderivative of this expression right here in the blue box. If it's e to the power of negative 2x, the antiderivative of that is going to be negative 1 over 2 e to the power of negative 2x. And then we'll put that in a bracket there, going from 0 to 1, and then I have a pi in front. Just to make this a little bit easier, I would recommend multiplying the constants together and pulling them outside the bracket. So that's going to be a negative pi over 2. And that's going all the way from e to the power of negative 2x all the way from 0 to 1. And now we're ready to use the fundamental theorem of calculus, where I can plug in my upper bound first. So that's going to be e to the power of negative 2 minus, and then I can plug in my lower bound here. So that's going to be e to the power of, well, negative 2 times 0 is going to be 0. And then in front I have my negative pi over 2. Right, from there, I guess we can just simplify the inside there. E to the power of negative 2 is just e to the power of negative 2, and e to the power of 0 is just 1, so minus 1 there. Now this is an acceptable answer. If you want to distribute the negative pi over 2 into the brackets, you can. You would now get negative pi over 2 e to the power 2 plus pi over 2. So this right here is another acceptable answer, but this answer above is also correct, and feel free to simplify as much as you want or not. Okay, let's move on to the next example here. Another disk question here. I won't read the original problem here, but here is my equation, y equals the square root of x plus 1, and I'm bounded between 1, 5, and y equals to 0. So a very good way to kind of maybe start off the problem is drawing a little sketch of what this diagram could look like. Since it's plus 1, you're shifting 1 to the left here, and then your radical opens to the side like that. And I'm looking at x equals to 1 and x equals to 5. So here's 1 and here is 5. And y equals to 0 is just this horizontal line in purple. And that's just a reminder that we're going to rotate this around the x-axis there. Now the area that's being generated between 1 to 5 is this region right here. And once again, that shaded region that's enclosed by these curves is going to be rotated around the x-axis, and then a solid will be formed, and we need to find the volume of that solid. Okay, so let's take a look at a few more visual diagrams here to kind of see what's going on here. If I take a look at this first diagram here, this has an x value of 1, this has an x value of 5, and this is the top part of the curve, y equals to the square root of x plus 1. And that's being rotated around the x-axis. If it's being rotated around the x-axis here, then if I take a look at this next diagram, we should have another shape that's very similar to the region just above the x-axis, so it's it's symmetric. And then if I take a 3D view of this object from top to bottom, this is what the shape will look like, another sideways cup. And here is another visual of what the object will look like, a 3D object. And if I go back to this image right here, I mean, I guess this would be like 1 roughly, and somewhere around here that would be roughly 5, I believe. So I think those are the boundaries, yeah, 1 to 5. And just like the previous problems, our goal is we need to find one of these disks that's inside this 3D shape. I want to calculate the volume of that disk. It looks like a sideways cylinder, and once we have the volume of one of those disks, we can find the volume of the entire shape by integrating from 1 to 5. Okay, so let's take another view of this object from the front. So we've done a few of these now, so you realize that we always start off with volume equals to pi r squared h. That's the volume of a cylinder. The height is just like, sorry, if I draw another, if I just extend this disk here, I mean, the height is just this region right here, which is just dx. So we can go ahead and update our height there. So volume would equal to pi times r squared times dx. After we have our dx, let's take a look at the radius right here. So the radius is, use my red marker here, this is my radius right here. That's r. And if you think about that, this distance right here, if I go from top to bottom, That's just the y height, right? So that y height will now represent the radius. So now my new volume is pi y squared times dx. And then ask yourself, what does y equal to? Well, y would equal to the square root of x plus 1. And that will replace the y right there. So now volume would equal to pi, brackets the square root of x plus 1, all to the power of, all to the power of 2 times the dx. And let's go ahead and simplify this. This is pi times the square root of, sorry, not the square root, but just x plus 1 times dx. So this right here is the volume for one of those disks. And if I want to find the volume of the entire object, I need to integrate. And I need to integrate from an x value of 1 all the way to an x value of 5. So that's the idea there for my upper and lower bounds. So let's go ahead and put a 1 and a 5 right there. And that right there is my volume expression for this particular disk. And now I need to evaluate this using the fundamental theorem of calculus. Well, the antiderivative of x is going to be x squared divided by 2 plus, and then the antiderivative of 1 is going to be x. And that's going all the way from a lower bound of 1 all the way to an upper bound of 5. And the pi can just remain on the outside there. All right, so now we have to evaluate this using the fundamental theorem of calculus. I don't see any quick shortcuts here, so let's go ahead and evaluate this with my upper bound first. So that's going to be 5 to the power of 2 divided by 2 plus just 5. So that is the first upper bound, and then I need a minus. I need minus the lower bound now, so 1 now goes in for the x's here. So that's going to be 1 to the power 2 divided by 2 plus 1, and then I can close the bracket here, and then I can close that bracket there. So unfortunately for this particular problem, you do need to spend a little bit of time calculating the individual numbers inside the brackets here. Hopefully we can do that slowly here. So this part right here, 5 to the power 2, that's going to be 25. So 25 divided by 2 plus 5 minus 1/2. And then minus 1. And then if you evaluate all of that, that's going to be 16 in the brackets. And then you have your pi on the outside. So my final answer is going to be 16 pi. And that's how you do that particular question. Okay, let's move on to the final question for the disk method for questions on the, let's move on to the final question for these disk problems when we're rotating around the x-axis here. This time I have the function y equals to sine x, and I am bounded by the following parameters here: x equals to 0, x equals to pi, and y equals to 0. So just like the previous problems, we can start off by graphing or sketching y equals to sine x, the graph that's given to you. Okay, and then based on my boundaries here, I have x equals to 0, which is right here, x equals to pi, which is right there, and then y equals to 0, which is just this green line right here. And that's just a reminder that I'm rotating around the x-axis, and the region that I'm focusing on is this red region right here. So that red region is going to be rotated around the x-axis, and that's going to form some kind of solid, and then we need to find the volume of that solid. Okay, let's take a look at a few visual diagrams, and then we'll set up our equations here. Okay, so here's my first visual diagram here. So this is going to be 0, this is going to be pi, and this equation right here is y equals to sine x. And we're going to rotate this around the x-axis. If I do that, then I get another shape just underneath the x-axis, which I'm trying to highlight here in red there. So we get another shape that's very similar to the top shape. And then this solid's being formed, and let's take a look at what that solid could look like. It's going to be a little bit hard to visualize here, even from a 3D view. From my 3D view, that's what it looks like. This is still 0, and this is pi. And our goal is if I can find the disk of 1, if I can find the volume of one of those disks, I can find the volume of the entire shape just by integrating from 0 to pi. Okay, let's take a look at a front view of this object again. There it is. Let me start off with volume equals to pi r squared h. And what is the height here? Well, the height is always going to be this sideways length right here, which is dx, the difference in x right there. So if I just kind of extended this disk right here, it's a sideways cylinder again, so dx is going to be my height. So my new volume formula is going to be volume equals to pi r squared times dx. Okay, once I have my height there, let's take a look at the radius. So this right here, that's my radius. And if I think about that from top to bottom here, that's just, you know, the y height. So now my y will now represent my radius. So let's go ahead and update my formula one more time. This is going to be volume equals to pi times y squared times dx. And remember, what does y equal to? Well, in the original problem, y would equal to sine x. So now sine x will replace the y. So volume equals to pi times bracket sine x all to the power 2 times by dx. So that is the volume for one of the cylinders, and if I want the volume for the entire object, I need to integrate this from, you know, of 1, I believe. Pi. There's no ones on the horizontal axis there, so I'm going all the way from 0 to pi. Okay, so my lower bound is going to be 0, and my upper bound is going to be pi. Okay, now before we can officially integrate this, we have to replace sine squared x with, or sine x all to the power 2, which is sine squared x with a identity from pre-calc 12. So sine squared x is the same thing as 1/2 minus 1/2 cos 2x. If I don't have this identity right here, I actually can't integrate sine squared x easily. So before I start integrating, we're going to replace sine to the power 2 with the identity there on the right hand side. Okay, so this is going to be 1/2 minus 1/2 cos 2x times dx. And now we're ready to find the antiderivative. The antiderivative of 1/2 is going to be 1/2 x. The antiderivative of cos 2x is going to be sine 2x, and then I need to times that by 1/2 here, and then we still have this negative 1/2 in front. So that's, you know, how you find the antiderivative there, and that's going from all the way from 0 to pi, and there's also pi in front. We may want to just kind of clean up the inside bracket here, so 1/2 x minus, now 1/2 times 1/2 is going to be 1/4, so 1/4 times sine 2x, going all the way from 0 to pi, and then a pi in front. And then we can finish this off by using the fundamental theorem of calculus. So upper bound first, so that's going to be 1/2 times pi minus 1/4 sine of 2 pi. That's the first bracket, and then minus, then I need to minus the lower bound now. Which is going to be 1/2 times 0 minus 1/4 sine of 0. And then all this is going to be multiplied by pi. One thing that you might notice is that this region right here just goes to 0. And I know that sine of pi is also going to be 0. So now I'm left with just the 1/2 pi, which is this expression right here. And that's being multiplied by this outside pi. And my final answer would be, well, pi times pi is pi squared divided by 2. So that's my final answer for that problem. All right, let's Let's move on to the next style of questions in the disk method here. And for the next question, I need to continue finding the volume of the solid generated when the region enclosed is revolved around the y-axis. All right, so we do have to take a different approach to these kind of problems when we're going around the y-axis, but it's still very similar to problems when we're generating them around the x-axis. Let's start off with y equals to the square root of x minus 1. Let's take a look at what that graph will look like. So here's my axes. And if it's a minus 1 here, that means the graph is being shifted 1 unit over. And then the graph will look like this. All right, so there's my graph of y equals to the square root of x minus 1. And now I'm looking at the boundaries of y equals to 0, which is right there, and a y value of 1. So I'm kind of looking at this region here. And now I have x equals to 0, which is this part right here. That's a reminder that I'm rotating around the y-axis there. And the area that's being generated, or the region that's enclosed, is this green region right there. So let's take a look at a few more visuals before we start finding the volume of this particular shape. Okay, so here's a visual right here of what the object will look like. Let me see if I can break this down here. So this red part right here was y equals to the square root of x minus 1. And it was being rotated around the y-axis. So we get this shape here that's symmetric on the other side. And I believe in the previous slide, I said that this region right here, which I'm highlighting in black, that part is being rotated around the y-axis. So you should end up with the same pattern or shape on the other side here. So that is the solid that's being generated. And if I keep on rotating this around the y-axis, I do get this solid shape where I can definitely find the volume of that shape. And if I take a look at a visual right here, this is roughly what the visual will look like. And from here, let's say this is the x-axis, this is the y-axis, and I guess this would be a height of 0 there, and the maximum height here would be 1. And my goal now is to find the volume of that 3D shape. Now for this particular problem, just kind of erase the boundaries here. You know, we do have this disk right here, and I'm just going to kind of extend it right there. So there's my cylinder right there. So my goal is, if I can find the volume of one of those disks, I can find the volume of the entire shape by simply integrating. Okay, so here are my steps here. I still start off with volume equals to pi r squared h. Now ask yourself, what does height represent? Well, height is the height of this disk here. So since we're taking the difference of the y values, this is dy. So dy now represents the height of my disk here. So anytime you're rotating around the y-axis, h is dy. And if you're rotating around the x-axis, h is dx. That's a quick way to remember how to replace h in your formula. So volume will now equal to pi r squared times dy. Great. Let me erase that. And after that, I need to find the radius of my shape here. And if I go right to the center here and go to the end here, that's my radius right there. And if you think about that logically here in terms of like the graph here, it's really representing a horizontal distance of x from the y-axis, right? So if I go from the y-axis all the way over here, that's just x. That's like a distance of x. And if I think about it from the other side, you know, if this is my y-axis, and if I go all the way up to the edge right here, that's also a distance of x. Okay, so that means my radius is going to be now x. So volume equals to pi times x to the power 2 times dy. Okay, so I'm almost done my setup here, and the question is, what does x equal to? Well, let's get back to our original problem. Our original problem was y equals to the square root of x minus 1. So I need to isolate for the x right here. And how do I do that? I square both sides. So now I get y squared equals to x minus 1. And then I have y squared plus 1 equals to x. So this x is going to replace that x right there. All right, let's go ahead and make that substitution step. So volume equals to pi, bracket, y squared plus 1 all to the power 2 times dy. So there is my volume expression right there. And if I had the volume of one disk, I can find the volume of the entire shape by integrating. And where am I integrating from? Well, if I go back to my visual diagram here, or if I go back to the beginning of the problem here, we're really integrating all the way from 1 to 0, or 0 to 1. And if I go back to the shape here, so we're going from a low bound of 0 all the way to a high height of 1. So those are my boundaries right there, from 0 to 1. Okay, let's go ahead and figure out how we can find the antiderivative of this expression, and let's go ahead and evaluate this. Step number 1, I would expand that. So that's going to be y squared plus 1 times y squared plus 1 dy, integral sign from 0 to 1 pi, and volume equals to that. All right, let's go ahead and FOIL this out. If I FOIL this out properly, I should get y to the power 4 plus 2y squared plus 1. And I'm still going from 0 to 1 of dy with a pi in front, and that's my volume. Okay, so now that I've simplified now that I've FOILed everything out, let's go ahead and find the antiderivative now. The antiderivative of y to the power 4 is y to the power of 5 divided by 5, plus the antiderivative of 2y squared is going to be 2y cubed divided by 3, plus, and the antiderivative of 1 is just x. Or sorry, not x, it's y, because I am taking the antiderivative with respect to y. Okay, so after that, I need my square brackets here, going from a lower bound of 0 all the way to an upper bound of 1, and volume would now equal to pi times all of that. Now, the good news here is when we're applying the fundamental theorem of calculus, we only need to consider the upper bound, because when we insert 0 for our lower bound, everything goes to 0, so we just need to calculate the upper bound here. So that's going to be 1 to the power of 5 over 5 plus 2 times 1 cubed divided by 3 plus 1. And if I go ahead and evaluate this, this will be pi times 1 over 5 plus 2/3 plus 1. If you go ahead and simplify the fractions and add everything up, you should get 28 over 15 times pi. And that's your final answer for that one. Okay, let's keep on moving along here. All right, let's take a look at the next example here. I want to find the volume of the solid generated when the region enclosed by the following curves is revolved around the y-axis. This time I just have y equals to x squared, and it's being bounded by y equals to 2. So let's take a look at what the diagram would look like. Okay, so here's my simple parabola. This is y equals to x squared. And so there's my parabola here. I'm just going to highlight in red one more time. We're going to rotate this around the y-axis, and we're also being bounded by a line of, I'll just say that this is y equals to 2. Okay, so if we're generating around the y-axis, we're going to be focusing on this purple region right there. Okay, so here's another diagram of that exact same situation here. This is y equals to 2, and this region right here in blue and purple, that's going to be rotated around the y-axis. And then if I take a 3D look at that, this is what the object will look like. So my goal is I want to find the volume of that particular shape. So this right here is y equals to x squared. Remember, if I rotate around the y-axis, I get this other symmetrical shape over here, and then I get this 3D object that's being formed. The bottom height here is 0, and I go all the way to a maximum height of 2, right? So this value of 2 is going to be my upper bound there. Okay, so let's go ahead and erase some of the colors here, and let's kind of think about our volume of our cylinder or disk. So pi r squared h. Okay, so if I go ahead and draw an expanded disk here, this right here is like the height, and that represents dy. So remember, anytime you are rotating around the y-axis, the height is always going to be dy. Okay, so that takes care of the h inner formula. And then for the radius, let's take a look at the radius now. The radius is basically from the y-axis all the way to the edge there. That's my radius. And if I think of that in terms of the function, that's just this horizontal distance x, right? So x is really the radius there. So volume equals to pi, and then that's going to be x to the power of 2 times dy. And then you have to ask yourself, what is x in this particular problem? Okay, so I know in the original problem, the function that was given to me was y equals to x squared. So I need to isolate for this x. So in order to do that, I would take the square root of that and the square root of that. So this would be the square root of y would equal to x. And now I can replace this x with, that x over there. And that's going to be volume equals to pi, bracket, the square root of y, close bracket, to the power of 2 times dy. And now that the y's match up, I know that my integral expression is going to be correct. If I keep on going here, that's going to be pi, and you'll notice that this squared and this root sign, they'll cancel each other out, giving you just a single y times dy. So that's the volume for one particular disk. And if I want to find the volume of everything, I'm integrating all the way from 0 all the way to a height of 2. Right? So from 0 to 2. So that's going to be from 0 to 2. And now I can find my antiderivative. The antiderivative of y is going to be y to the power 2 divided by 2. That's going from 0 to 2. And then I have a pi in front. This one's really nice to evaluate because the lower bound here is going to be 0. So we just need to concentrate on the upper bound. So that will be y. That's going to be 2 to the power of 2 divided by 2. And a pi will be in front. So 2 to the power 2 is going to be 4. So 4 over 2. And my final answer is going to be 2 pi. So that one there worked out pretty nice for a final answer, and the overall procedure wasn't too bad. Okay, let's do one more problem here, and then we can finish this video on the disk method. Okay, so we've got quite a bit of visuals for this one here. So once again, I need to find the solid that's generated when the following region enclosed is being rotated around the y-axis. So my function here is ln x, and my boundaries are y equals to 0, y equals to 1, and x equals to 0. Okay, so here is the function y equals to ln x, this particular graph right here. I believe this point right here is 1, 0. And let's take a look at some of the boundaries that are given to us in this problem. This horizontal line right here, that's y equals to 0. And this line right here is the line y. This is going to be the line y equals to 1. And we're also being surrounded by x equals to 0. So that's a reminder that we're rotating around the y-axis, and that means the area that's being enclosed is this orange area right there. So that orange area right there is being rotated around the y-axis. Here's a better view of the region that's being enclosed between y equals to 1, y equals to 0, and x equals to 0. And if you think about it logically, you're going to have a symmetric shape on the other side of this axis here. So that's something that you'll probably see right there. That's like the kind of the shape, and that's being rotated around numerous times until a 3D object is formed. And there's another view of what I was just talking about. And if I take a bird's eye view of this, that's the shape of the object that's being generated. And yeah, so let's go ahead and find the volume of this particular shape, right? So remember, if we can find the volume of one of these disks, we can find the volume of everything by simply integrating. Okay, let's go back to a front view of the object here. Let's start off with volume equals to pi r squared h. And remember, if this is an imaginary disk right here, this represents the height of the disk, which is dy, and anytime you're rotating around the y-axis, as mentioned, the height is always going to be dy. Okay. All right, let's get rid of that now. And then we're going to find out what is the radius. Well, if I take a look at my diagram here, this is the radius right here. And that represents, the horizontal distance from the y-axis all the way to the edge, which is kind of represented by x. So my x is my radius. So volume equals to pi times x to the power 2 times dy. And then you have to ask yourself, what does x equal to? Well, in the original problem, y would equal to ln x, and we need to isolate for x in a way. So I can raise both sides to the power of e. So I have e to the y equals to x. And then I can replace this x with that x. Okay, so volume equals to pi, bracket e to the y times dy. So that is my volume expression for one disk, and I can go ahead and find the volume of everything by simply integrating. And if I'm integrating, I'm going from a height of 0 all the way to a height of 1. And that's kind of given to you in the original problem as well. You're bounded by, if you go back to the original problem, these guys are your upper bound and lower bounds there. So this is your lower bound, that's your upper bound. Okay, so going back to my volume formula here, this is from 0 to 1. And if I multiply the 2 and the y, I get e to the power of 2y dy, integral from 0 to 1 of pi, and volume equals to all that. Okay, let's go ahead and find the antiderivative now. The antiderivative of e to the 2y is 1 over 2 e to the 2y. And that's going all the way from a lower bound of 0 to 1. And then I have a pi in front. My recommendation is I would take the constant of 1/2 out and multiply it with the pi. So that gives you pi over 2. Just pull the constant out, and you have e to the power of 2y all the way from 0 to 1. And now you're just using the fundamental theorem of calculus, starting with your upper bound. So that would be pi over 2 onto e to the power of, well, 2 times 1 is just 2, minus, and then if I plug in 0 for y, that's e to the power of 2 times 0, which is 0. And now you just kind of finish this problem off. This is pi over 2 times e to the power 2 minus 1. And that right there should be enough to get the full points for that particular question.